Okay, hello everybody. It is a great pleasure to have today Assaf Naor from Princeton University, who will speak to us on an integer parallelotope with small surface area. Assaf, thank you, and the floor is yours.
Okay, thank you very much. Thank you for the invitation. What I'm going to do today is I'm going to explain the proof of the following theorem. This is joint with Oded Regev from earlier this year. It's on the archive. And so it states the following, that for every n, for every dimension, there is a convex body. Okay. Such that if it tiles are n, so k plus z to the n is all over n. If you shift k by elements of z to the n, you get all over n. It's a tiling, so I guess x plus k intersected y plus k has empty interior. You can only touch in the boundary, empty interior. If x and y are these integer shifts and they're different, of course, and the surface area of k is at most n root n roughly. There's a little O term, which I will discuss later. Okay, so that is the theorem. Very simple to state, and I'm going to explain a little bit where this is coming from, and then just prove it. And that's my plan for today. Just in terms of the title of the talk, so if you have lambda, and we'll need to deal with lattices later. So if you have lambda, or maybe before that, I should say that from this fact, from the fact that k tiles are n, a little exercise, you get that the volume of k must be 1. So just by that, so this is just from tiling. Has nothing to do with convexity. It's an exercise, so it has to have volume 1. This is because the co-volume of z to the n, the lattice, is 1, and therefore by the isoparametric theorem, the surface area of k is at least the surface area of the Euclidean ball divided by the volume normalized to have volume 1, which you can compute is root n. So Bn from now on is going to be the Euclidean ball, standard Euclidean ball. Okay, so up to this little O of 1 term in the exponent, this is the best you can hope for. And the obvious open question, so obvious question is, can we improve this? So less than a universal constant multiple. Whenever I write less or equal to the twiddle, I mean just really 100, some universal constants. So can we improve? And that would, of course, be equivalence up to universal constants. Okay, so that's the obvious question that remains open. I personally think that it would be much nicer if what was the question?
You mean the surface area?
Of course, yes, yeah. So in the same statement, but getting the best you can hope for, which is a minimum, the up to constants, what you get from the isoparametric theorem. I personally would be very happy if the answer is no, that there's some that you cannot get it, but I see no reason to expect that, and maybe there is a construction which gives a root n. All I can say when we'll go over the proof, we can discuss this, is that I don't think it's going to come from the way we're proving this. Okay, so but maybe there's a way to prove that you cannot get it exactly to be root n, and that would be even nicer in my opinion. Okay, but the obvious question, and we'll see where it's coming from and what is the bottleneck in the proof. And I I think this is a real bottleneck. It's not just going to be mechanical. That's just my. But we'll get to that. Okay. So now, just to explain the title and also introduce a little bit of facts about lattices, because we will deal with other lattices later. We'll see that we need to for our approach. So if you have lambda in Rn is a lattice, so it's the same thing as if you want lambda is some I goes from 1 to n z xi or x1 rank n, x1 up to xn are independent vectors, linearly independent. Okay, so if you have a lattice, then a convex body K, this is standard terminology, is called a lambda parallelotope. That's parallelotope if it tiles Rn by lambda. So if Rn is lambda plus k, and again x plus k intersected y plus k, k has empty interior. Forever. So that's the standard terminology. And when I say when lambda is z to the n, then this is what we had before. That then we say then k is called an integer. Parallelotope. So really, this is I don't really want to waste time, but that's time. The obvious for integer is k is minus a half the cube to the n. Indeed, it has volume 1, but in this case, the surface area of k is 2n. So I think the best known, people looked at this question before. I'll mention a few words about it. So the best previous bound was due to a Feige Kindler and O'Donnell back in 2007. There was a very nice conceptual idea in this paper, which I will get to later. And they just found there exists k, they proved that there exists k such that they improved this by a constant factor, something like 1.237, something like that. Okay, so it was not known before. So when I say exists k, which is again an integer part of it. Okay, so that was the game. I'll explain later where I came, when I became interested in this, and actually from their paper, but there will be other things. Just really, I want to get to the proof. So, but a little bit of history. So there is a very nice theorem, a precursor to this of Kindler. O'Donnell, Rao, and Vigderson back in 2008, and they proved the same thing without this convexity requirement. So there exists a compact set, omega, some compact set which no convexity requirement, a compact set omega in Rn, such that as before, it tiles Rn. So Rn is the same thing as omega plus z to the n, and as before, disjoint interiors, empty interior, and the surface area. So this again forces the volume to be 1, and then they got the surface area to be the best you can hope for, root n. So n to the 1/2 without the little 1 term. They were motivated by a certain computer science application. I might get to it in the end. It was actually, if such a set is used to prove that some algorithm is impossible. So it was used to prove an impossibility result. And for that, convexity is completely irrelevant. So there is no need for convexity. Their paper, the result is what they needed, and it genuinely produces something not convex. So their set really looks like an amoeba. It involves some you start with some initial set and you move it randomly, and take randomly many copies. So it's a random construction, and the set is not convex what they propose. It looks like really an amoeba that succeeds, or some complicated shape which when you shift it by z to the n, the tiles are in, but bumps go into each other. So it's really not the way you imagine a convex tiling over n. But I want to make it completely clear that for the application, it's completely irrelevant if their set is convex or not. So this is not something that they needed. However, also historically, in the area of tiling, people always prove theorems first about convex sets. People are interested in both cases. I remember when I think it was O'Donnell who gave a talk at a conference in Edinburgh back in 2008 when he announced this. I think everybody in the room asked, "What about convex sets?" So this was in the mind, just geometrically interesting for people in the audience, and it was a known question. It's something that I certainly thought about for a long time. But as I said, I do not have an application of it, and I will discuss some speculations about applications later. Okay, so this is really for geometry, for the purpose of geometry. Okay, and I do not know any use for the fact that the set is convex, other than it's a natural way, it's a natural type of tile to look into, to try to find. There were other proofs of this. Alon and Clarta gave a nice proof of this. I should say that all of these approaches are really there is for the algorithmic application. So the idea to connect these two algorithms is this paper of Feige, Kindler, and O'Donnell, which is really the paper that changed everything. Prior to this, people have been looking at these kinds of questions from the point of view of crystallography, maybe mainly in R3, and the connection to algorithms and the renewed interest is due to this very, very nice paper of Feige, Kindler, and O'Donnell. They realized that they proved that if you could find such a set, then you could fool a certain algorithm called parallel repetition. And Raz, a year later in 2008, actually proved their application without constructing this set. So, and really what Kindler, O'Donnell, Rao, and Bigderzohn did is understand Rao's proof, which happened in the discrete world, and did a continuous version of it. So there were many people contributing to this, and this was a very nice story. I want to say maybe one very other small thing about what is known. There is a very nice paper that you can, it's from 2020, it's on the archive of Braverman and Mincer. From 2020, which they proved that if you want omega, so if omega in our n is compact, tiles are n by z to the n. So the shifts by z to the n tile are n, and is invariant under permutations of coordinates. Okay, so you permute the coordinates. If a point is in omega, it's still in omega. Then you cannot do this. Then the surface area of omega is at least a constant, universal constant multiple of n over root log n. So, but this is, but you can, and you can achieve and exist such omega with these symmetries with. Okay, so that is another, so if you add symmetries, then the answer becomes n, roughly n, but you can shave off a root log n, and that's the best you can do. So that's a different direction, but it's a very nice paper. If you add symmetries, and you can imagine many other things that can be asked in this area. I will not get to those speculations. I want to get to the proof. So I want to say a few things about. So there something about which I would be. Yeah, I would be happy. So there's when you see the proof, when somebody proves to you that there exists such a set which is not convex, it's some complicated looking set with this property, you can ask yourself, does this give evidence that there should be such a convex set or not? So my initial intuition would be yes, right? Because if a set has small surface area and it looks something like this, the tiles are n, then of course the surface area is only bigger. So there should also be a convex set with this property. However, there are many more general compact sets that not convex, the tile are n, so there is a bigger space, and this is actually a huge restriction. So Minkowski in 1897, he has two theorems about parallelotopes, beautiful theorems. So actually there's a complete characterization of when a convex body is a so it proves two theorems. First of all, there is a full characterization of when a convex body in Rn is a parallelotope. So firstly, it has to be centrally symmetric. Second, every one-dimensional face as well. And the third condition is that if you take any n-2 dimensional face, so every face of dimension n-2, so it's a n-2 dimensional plane, you can look at its orthogonal complement. It's a 2-dimensional plane. And you can look at the orthogonal projection of your convex body onto that 2-dimensional plane. So for every n-2 dimensional face, look at the orthogonal complement, it's a 2-dimensional plane, and project your convex body orthogonally onto it. And then you must be able, it turns out, Minkowski proved that what you see is either a parallelogram or a centrally symmetric hexagon. And this turns out to be if and only if. So this is a complete characterization, a very nice, beautiful theorem of when a convex body is a parallelotope. And the other thing that Minkowski proved is that there are finitely many combinatorial types of parallelotopes in Rn. So there are finitely many, at least it's still infinitely many as you run over all possible lattices, but there are finitely many combinatorial types. So number of vertices, number of faces of every dimension, etc. So if you start with this amoeba that was proved by, whose existence was proved by Kindler, O'Donnell, Rao, and Wigglerzone, you want to somehow make it still tile or n and become convex, and you think you would make the surface area smaller. I could not figure out how to do this formally. And I actually think it would be fascinating if somebody finds a way to start with a non-convex shape and massage it. You'll have to fall into one of these finitely many combinatorial types, and you're going to have to satisfy these algebraic requirements that Minkowski found. But so I think it would be, maybe it's impossible to just take it formally as a black box, the fact that this amoeba exists, and get a convex body. If it is possible, I'm sure the procedure to do this would be useful for other things. But again, I never had any idea of how, could figure out even how to begin, because of this. It's a very rigid, it's a severe restriction to be a convex parallelotope. Okay, so I think trying to deduce it from their proof would be very nice. The proof I'm going to show you that Regan and I found is completely unrelated to that proof. We're not inspired by it, and it's completely unrelated. And I think, but I think it would be very interesting to actually to relate it. As I said, if maybe it's impossible, but it would be a valuable contribution. So okay. Now, again, so in terms of things that I'm wondering about, 30 more seconds before I start jumping into the proof and explaining to you where we got this thing from. Okay, so as I said, in the algorithmic application, there is absolutely no use for the fact that the convex body is symmetric. The tiling, this tiling set with small surface area is convex. However, I can imagine there are things that have to be worked out. I can imagine applications if the convex body that we say that from the main theorem has the property that you could optimize over it, that you can compute efficiently the maximum of every linear functional on the convex body. So question, can one construct a K as in the main theorem an integer parallelotope with surface area up to little o terms of root n, on which one could optimize efficiently. So again, by that I mean the input, it's an algorithmic task. The input is a linear functional, and then you want to evaluate its maximum. So that would be probably useful, but again, details have to be worked out. The proof that I'm going to show doesn't even come close to it, to producing such a concrete, nice body. It's nothing like the cube. For one, it has to have, so any such K must have polynomially many faces. This is because you can improve. So here's a theorem that. So this is something. It's part of a work in progress with Kifbal, Kawai Bowotsky. So you can improve the isoperimetric theorem for polytopes. So it's not a huge surprise, but you have to prove something. If K in Rn is a polytope with m faces, then if you look at the isoperimetric theorem, so you look at the isoperimetric quotient of K, the isoperimetric theorem says that the lower bound is root n, but that's only attained when you're a ball, or roughly a ball, a Euclidean ball. If you restrict to have m faces, then you get what you expect, which you get root log 2n over n. Yeah. So if m is exponential and like a ball, you get root n, but you can get better. But in particular, if the surface area is root n, it forces m to be exponentially large in n. Not a huge surprise, but we should say it. So I mean, anything with small number of, so it's nothing like a cube. A cube is 2n faces, and indeed you can optimize over it. So if you cannot get polynomially many faces. So if you can construct such a body on which you can optimize, then it will be an interesting reason why you can do that. It will not be just because it doesn't have, it's defined by polynomially many linear inequalities. And then, okay, there are more open-ended things from the Banach space perspective, which is where I'm really what is powerful from the theorem, the parallelotope? It's small from theorem, from the main theorem, is centrally symmetric. So the unit ball of a norm is this norm good for? What is this norm? What is this norm? Or okay, I'm really, what is it good for? So it's really, the tiling condition is an interesting property of the basis, and you can write it down and you can stare at it. And I have not seen an application or in the context of classical Banach spaces of what does this mean that the unit ball of a norm tiles are n by shifts of z to the n. And I just, my hunch is that this is good for something. This is a counterexample to some conjecture. It can be used for something. This is an interesting norm which we construct in a funny way. And I would be happy to just understand what does all of this mean from the point of view of Banach spaces. There are other motivations. There's applications from the context of nonlinear equations, extensions of Lipschitz functions, etc. I will stop all of this and I want to jump into the proof. Okay, I think it would be interesting. The main thing is to get rid of root n, to get a read or prove that you cannot get rid of the little O1 term in the main theorem. If you could get it to be optimized, I don't know if maybe it's impossible to get a nice body in which you can optimize. That might be useful for algorithms. And generally, from the Banach space perspective, this is an interesting object, and I would be happy to see what it means and what it's good for. Okay, so I want to go into the proof. And I'll start with the idea of proof, and then I'll explain details. Okay, so the starting point is something obvious, something that we knew all along. This is not something from, is something that was known for a long time, is that the problem is trivial, is easy, okay, I don't know, easy, for a generic lattice, if z to the n is replaced by a generic lattice. So you take a lambda parallelotope, you search for a lambda parallelotope with small surface area rather than an integer parallelotope. Okay, so there is some, and the reason for lattice. Okay, so, and the reason for this is so what do I mean by generic lattice? I want so we want what's called a good lattice. So so it's easy for a good lattice, and by that I mean a lattice lambda whose covering and packing radii are proportional, are within group one of each other. So by that, so if you have some lattice, so there it has two natural parameters. One of them is the covering radius. So you want the smallest r. If you draw a ball every lattice point of radius r, the union of all of these balls is all of space. That's the covering radius. And the packing radius is the largest little r, such that if you draw Euclidean balls of radius little r around each of the points of the lattice, the balls are disjoint, they have disjoint interiors. Okay, So for Z to the N, the covering radius is 1. The covering radius is root n, and the packing radius is 1 of order. And that is, but this is not what happens for a typical lattice. So Rogers proves in the 50s that such lattices exist. There are other proofs, but really there is the space of all lattices can be identified. So you look at SLN of R modulo SLN of Z. So this is just, if you take an element T in SLN of R, then the lattice, the corresponding lattice is T of Z to the N. And of course, you can mod out the SLN of Z because you don't change anything. And so this manifold is finite volume. So there is a Haar measure on it, a Haar probability measure on it. And if you choose from the Haar measure, and then with probability 1, you're going to get, and that's what I mean by a typical lattice. So if you choose a T from that Haar measure and apply it to Z to the N, then what you get is a good lattice. Okay, and, this is, I don't know who proved that for the first time. I think the first time I've seen it is in a talk by Margulis when I was back in Courant, but I mean, I didn't, but in any case, so that's what I mean by a generic lattice. So for a generic lattice, the problem is easy, and this was known for a very long time. Okay, so it's not so the reason for this is the following lemma, easy lemma. I'll prove it to you in a second. It says that when you have a subset over N, which is a convex body, and you know that it contains R times the Euclidean ball, then the volume, the ratio of its volume of its surface area to its volume is at most N over R. Okay? And the reason for this is just because, well, how do you compute the surface area? You say you take K and you add to it a little delta times the Euclidean ball and just use some proof. You use this inclusion here to say that this is inside K plus delta over R times K, which is the same as 1 plus delta over R of K. This is where I use convex. K is convex in the assumption of the lemma. And then, of course, in the volume of the boundary is the limit as delta goes to 0 of K plus delta. And if you use this inclusion, then you get that this is at most 1 plus delta over R to the N minus 1 over delta times K. Sorry, there's a limit, which is what I said, delta over R times the volume. Okay, so that's the proof of the lemma. But now let's stare at the lemma. Not writing anymore. This lemma says that a typical lattice, because it's a good lattice, will have you can take, so okay, so if lambda is a good lattice, and we can always normalize of covolume 1, then simply don't do anything. Don't take a complicated set. Then consider its Voronoi set. So this is just the convex body of all the points in our N, whose nearest point in the lattice is the origin. So with that, the Euclidean norm of X is less than the Euclidean norm of X plus Y for every Y in the lattice. 0. So that's obviously a convex set, and then just because it's covolume 1, it means that the volume of K is 1, but it's a good lattice. Because the volume of the Euclidean ball grows like a constant over root n to the n, this forces K, this is an exercise, K must contain some constant multiple of root n times the Euclidean ball. This is just a normalization. That this is just because I normalized things so that the co-volume will be 1. Okay, again, exercise. If you want to see, ask me in the end. I'll show the proof. Okay, so and so you can just apply the lemma, this easy lemma, with R is C root n, and you get that already the Voronoi cell, nothing special, but is at most n over R is of order root n. So you're done. So for a typical lattice, if you take a lattice which is a good lattice, the packing radius is proportional to the covering radius. Normalize it to have volume 1, co-volume 1. So its Voronoi cell has volume 1, or any set of tiles is volume 1. This is just a normalization. Then the Voronoi cell itself already is a convex set, which tiles by lambda by definition, and has surface area by this little exercise in convexity of order root n. Okay, so is that clear? So this is all I'm saying is that not for Z again, that's not the lattice we care about, but for a generic lattice, this was not an interesting question. Is that clear? So our starting point is to say, even though this was not an interesting question, let's try to use it anyway. Okay, and so the strategy, and then I'll show you the details, and we'll arrive at what is needed. So the strategy, which is really, I don't know, kind of the most natural thing that you try to do, in my opinion. So what we're going to do is we're going to try to prove by construct K by induction and dimension and the dimension. Okay, so how are we going to do it? We take some B to be a matrix. We'll slowly derive what we need from it. So it's an M by N matrix. So M is some number less than N. So I want to apply I want to apply the induction an N. And let V be the span of the rows. So V perp is the kernel of B. And let's look at consider the lattice, the sub Z to the N initially intersected with V perp. Okay, so V perp is I should have said the dimension. Suppose also that it has rank M. Okay. So the dimension of V perp is it is N minus N. Okay. So you intersect Z to the N with some subspace in diagonal. Typically, this will be completely uninteresting, right? There will be the subspace will be defined by all kinds of irrational conditions, and it will simply not touch Z to the N, except at 0. But okay, let's consider it and try to say something about it. So suppose that Z to the N intersected V perp does not have any short vectors. Any short vectors. short non-zero. Okay, so within the subspace V perp, I have some lattice, and it satisfies the assumption of the lemma, which is here. It's the Voronoi cell. Having no short vectors means that the Voronoi cell contains a big Euclidean ball. I didn't say what big was, but let's suppose R is big. We'll try it. We're just stating the intuition at the moment, and parameters will be explained. Everything will be done formally in a second. So, so if it doesn't have short vectors, then Voronoi cell of this lattice Z to the n intersected with V perp will work by what we saw. Will work. So will work within the subspace V perp. Okay, if R is large enough. Okay, so that's just what this little computation. That's what we just saw a moment ago. Okay, but that's not every. That is this. What does it mean? That's a subspace within V perp. We want to get a tiling body of all over n. So we want to do it by induction. So what we do is we look at the orthogonal projection onto V. V is the orthogonal complement of the kernel. Okay, of V. So it's a span of the rows. So project Z to the n onto orthogonally. And now again, for a typical V, this will not even be a lattice. If you project Z to the n into some irrational directions, you're not going to get a discrete set. So again, we need to make sure that everything is fine. Suppose it's a lattice. Okay. And now we'll apply B to it. The matrix B was the m by n matrix. So you okay, so suppose that this is a lattice. I'll have to make sure it is when I actually apply the proof. But now, suppose you set it up. This is not automatic. It's even rare that this is a lattice. And then apply induction. So this has rank m, like the rank of the matrix B, and B was m by n. So this is inside Rm. So apply induction to get a parallelotope K2. So then the Voronoi cell, I should give it a name, what I got here. K1, that was the subset that I get within V perp. Let's say call it K20, it's inside R to the m with small surface area. I need to get a body inside V, inside Rn. So just notice that if you restrict B to V, because V perp was the kernel, this is actually invertible on V. So I can apply the inverse of this to K2. Perp, call this K2. So this is, I'm allowed to invert because V was defined to be the orthogonal complement of the kernel. And then take K to be K1 times K2 with respect to the identification over N, V times V perp. Okay, and what you see is that the surface area of K, what happened? So here you got something small because it had no short vectors. For K2 perp, for K20, you got something small because it has no short vectors, but you lose something when you apply the inverse of the matrix, and when you have to compute, and we will in a second, what you lose is the norm of B, the operator norm of B. So when you but hopefully B has small operator norm. Hopefully all of these works together, and you can proceed actively. Okay, so what are the issues and to consider, and then we'll see how we just solve them. So there's a lot of issues with this hand waving that I didn't do anything yet, but what I'll do next is just formalize everything. So first of all, Z to the N intersected V perp has to be a lattice, so it has to be sufficiently rich, whatever that means. So this is something arithmetic, right? 2 Z to the N must have no short vectors. Again, something arithmetic is that this projection, orthogonal projection onto V of Z to the N has to be a lattice at least. So in order so that we can do the induction. And 4, I thought because we applied this B inverse to make everything B in our N, which we have to, B has to have small operator norm. Oh, I should have said that there is a little, it's abstract nonsense. It's following the definitions. You have to check that when you do this procedure, K will indeed be a tiling body. But this is just by design. That's why I had to apply the inverse. K1 was a Voronoi cell of the intersection with the orthogonal complement. K20 was by induction a tiling body. So this is really not, there's no idea involved. You just have to trace the definitions. This will always produce a tiling body over N. Okay, I'm not hiding any idea here, but you have to check it. Okay, and 5. Okay, there's a huge issue here, which is I wanted to apply induction, but I applied the inductive hypothesis to what? We applied inductive hypothesis to the lattice, what was it? B times the orthogonal projection, which was inside Rn, right? B times, that was just, we had no choice if we wanted to get a tiling body. But this is not, this suppose I made it be a lattice, and it will be a lattice. But this is not Z to the M. So I need to make a stronger inductive hypothesis for a bigger class of lattices. After one step already, you leave Z to the M, you have a different type of lattice. So you need to figure out what is the theorem you want to prove for other classes of lattices in order to apply induction. So we need a stronger induction hypothesis, inductive hypothesis. So these are the issues with this approach, and let me show you how you fix them. So okay, so when should I end, Beatrice?
We can take
5 more minutes.
It's fine. I had a question regarding the last issue.
I'm going to show. Yeah. Okay. Yeah.
Yeah. Is the issue here if you try to transform back to the integer lattice that you lose control of the surface area? Is that the thing?
Yeah. 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 And I have when I took this body here. So K20 is whatever I got. Applying B inverse, there was where it's inverse. What happened here?
Mm-hmm.
Okay. Applying B inverse is we have no choice. That is what will make K be a tiling body, the product set. Okay. So yeah, you can transform it artificially. Suppose you got it to be artificially to be Z to the M because it's a rank M lattice. But then this transformation, the change of basis matrix, I know nothing about. It's yeah, what it does to the surface area, you have to track. There's the norm of that, and that could be complicated. Okay, so I want to just solve all of these problems. And so, first of all, so it turns out that okay, so in order to get item 1 and item 2 and item 3, which are just to make these sufficient lattices, it's enough to take B to be a matrix with integer entries. It's actually what we need here. So we'll take B to be an M by N matrix with integer entries. And then there are things to check. They're all checked in the paper. They're all like little exercises in linear algebra. Okay, so to get item 2, in order to get that it has no, again, easy facts, all of these facts in linear algebra, so B is like this matrix M is less than N. So it's like a short and long. So if no S of the columns of B have are linearly independent. Sorry, if any S of the columns of B are linearly independent, then this, and that's just an exercise. Whereas item 2, then Zn, then, okay, sorry, I didn't say what I, okay. Okay, then, okay, I'll say Zn modulo intersection with B perp will have no short vectors, no vector shorter than root, what is it? It is root S, no non-zero. And that's just because this translates, and again, just linear algebra, that every non-zero vector in this intersection must have at least S non-zero entries, but they're integers. So their length is at least root S. The length of any non-zero vector, it has at least S non-zero entries, and all of them are in integers. So its Euclidean length is at least root S. So okay, but I didn't say, I should have probably said item 5 first, which is what is a stronger inductive hypothesis. Because so maybe this is the notation. We're gonna prove the theorem for not for Z to the n, but for any sublattice of Z to the n which has full rank. So let Q of n be the smallest Q, smallest quotient, such that for any lattice, sublattice, lambda of Z to the n, so it's a lattice consisting only of integer vectors of full rank, there exists a lambda parallelotope K with surface area divided by K, by the volume of K, at most is Q. So this is something a little funny. When the minute we generalize the theorem we want to prove to general sublattices of Z to the n, they no longer, their parallelotopes no longer have unit volume. So we have to normalize somehow by the volume, but we normalize by the incorrect power of the volume. And we don't make it homogeneous of order scale invariant. We divide by the volume of K, not the volume of K to the power n minus 1 over n. So and the reason is that this ratio here tensorizes. So this is just a little exercise that if you take K1 times K2, so in two orthogonal subspaces, partial, the surface area divided by K1 times K2, then this is just equals. So this will help us with the induction. This is the right quantity to look at. Okay, but this is somehow not scale invariant anymore, and that's inherent to the proof. Okay. So and then in the key lemma is that I have some conditions. Recursion that I wrote down gives that m is less than n, then q of n is less than 2n over root of s plus q of m, the norm of b. The operator norm, this is for every b in m by n with integer entries of, let's say, rank m, such that any s columns of b are linearly independent. Okay. And that is simply an implementation of the strategy that I said before. You take B, you look at the span of its the orthogonal complement of its kernel, intersect it with, you have a general sublattice of Z to the n, intersect it with the kernel of B. That will not have any short vectors because of this linear independence assumption. So you can apply the lemma that the little volumetric lemma that I proved before. And now you project orthogonally the lattice lambda from this notation. You project it orthogonally onto the span of the rows of B. Again, because B is an integer matrix, this will actually be a lattice. Apply B to that lattice, you get a full rank lattice of Z to the M, sublattice of Z to the M. Apply the induction hypothesis, take it back to Rn by applying B inverse, which is allowed because B is invertible on the span of the columns of the rows, and then the additive term is just this additivity property of the ratios. So you bound and you just check the detail. What I told you after I told you this strategy, everything that remains is just checking that it works. And this recursion, when you solve it, gives n to the, it gives q of n is less than root n e to the root log n, some constant. Okay, so you have to solve it, and this is what it gives. Okay, so the whole meat here, after you have this strategy, is how can you get such a B with this linear independence property and small operator norm? Okay, so our time is up. Let me tell you what the constraints are and the proof. And we do not know what is the best parameters here. What are the best parameters here? And it would be very nice to. I'll tell you what the question is. But this will not, even if you get the best dream parameters for the best possible B, this integer matrix that we're looking for, it will not improve the e to the root log n. It will not get rid of the lower order term, because we have in each step, because of this factor 2, we lose a constant. The worst we can lose is a constant factor. And the best we can lose is a constant factor. Okay. So if you do this log n many times, you lost the power of n already. So you need to do less than log n many times to get a root n here. And yeah, so I don't think that this inductive approach, even with the best parameters on B, will work. yeah, there are all kinds of things to try. We can maybe discuss the questions, but let me tell you what are the issues of B, and this is the question. So the question that I want to ask is, what are the parameters here? So given M and integers, and okay, there's a C, what is the largest S, which depends on these things, N, M, and C, such that there is a matrix B with integer entries, any S columns of B are linearly independent, and the norm of B, the operator norm of B from L to N to L to M, is at least C root N over M. Root N over M is the best you can hope for. And this is a very easy fact because, right, remember our weather matrix B, which was M by N, and we want every S of the columns to be linearly independent. So forget about any S, just make any column be non-zero. Okay. If every column is non-zero, there are M rows and N columns, it means that there must be a row with at least N over M non-zero entries. Right? Because if every row had less than N over M non-zero entries, there are M rows, you would get the total number of non-zero entries in the matrix is less than N. And the only way this can happen is if one of the columns is just completely identically zero, right? But the minute you have one row with N over M non-zero entries, they're all integers, its L2 norm is at least root N over M, which means that the operator norm of B is at least root N over M. And the question is, how large can you make SB so that you can get the trivial low, to get a matrix with operator norms at most root N over M. So times 100, let's say. So we give some bounds, which they may be optimal. I do not know if they're optimal, using a probabilistic construction, but I don't. But this is just a very nice geometric question about norms of matrices, which I do not know the answer to. So I actually thought I'd have much more time to even show the proof of the B that we got and compute all the details, but as usual, I didn't. I'm happy to show any details of the proof when I stop. And anyways, everything is online. And I did say all the ideas. So what remains is really linear algebra, just checking definitions, things of this type. So I'll stop here, and I'm sorry I'm over time.
Okay, thank you very much. Definitely explaining the ideas was great. Are there any questions or comments?
Assaf, can you say something about some other geometry? For example, what is the radius of the ball inside this guy?
It's going to be because we're off by little O terms. So if it will be up to little O terms, it will be root N. But there's little O terms which I don't know how to get rid of. So inside the body, it will have, just because of this initial step, just within the, oh, I see what you're saying. No, so I don't know actually. No. I would bet, I don't know. No, I do not know what is the rate. It should be root N, but I did not think about it. And at least on V perp, you have this root N roughly. And then, oh yeah, that's actually enough. Just because on V perp there is no short vector, then it means that okay, actually I do not know. So right, it's a product of Voronoi cells, but we distort them, right? We apply the inverse to each of them, and the dimension goes down. So we do not get you're asking a good, these are all legitimate questions. I simply didn't give them any thought before. I'm quite sure that if I do, I will be able to say something, but I do not know a lot about the geometry. I said that it has many faces. That was this, just because of this improved isoperimetric theorem for polytopes. Yeah, yeah. But it's likely that what you're asking is not a hard question. That's my guess. It just, somebody has to think about it.
Any more questions or comments? The parameter of surface area is because of the original algorithmic application, right? That they would like to control the surface area, not some other intrinsic volume, for example, right?
Yes, that's just because. So first of all, this is not just because of that. So if you look at the isometric question in R3, this is the mathematics behind this thing about dimension going to infinity, getting things up to constant factors is very modern. But this is actually an issue in crystallography, in R3 even, or you can ask among all sets that tile R3, which one is smallest surface area. The surface area that shows up there is really from physics.
I see.
Okay. It also shows, so that's interesting. Having said that, you can ask about what is the smallest mean width of a parallelotope, etc. And people have been studying this. So there are papers, I think I gave references in one of in the paper, there's a reference to the question of mean width. You can definitely ask this. But the reason I'm interested in surface area here is because of the computer science application, and also because that's the right thing to look at if you're thinking of an n-dimensional crystal or something. But usually from the point of view of physics, you want the exact minimizers, and that's not known and very delicate and a very, very, very old question. Actually, it's a conjecture of Kepler. So this is very, very old mathematics. We are doing the up to constant versions and dimension going to infinity versions of it. But surface area comes from physics in low dimensions.
Okay, I see. It's the natural quantity to look
Sphere
for.
packing, yeah. But it also, this is what shows up in the computer science applications, and it also shows up in other nonlinear applications that I've been studying. But yeah, you can definitely ask about other intrinsic volumes, other parameters. There is a lot to do here. Look at in the paper which is online, there is a reference to the solution of the exact minimizers in R3 for mean width, which parallelotope is smallest mean width. So that, not even up to a constant, the exact minimizer that has been done. I'm in the name of the person is in the top of my head, but I forgot. But it's in the paper, so that's a good place to start. But I'm quite sure that most of the questions that occur to anybody are natural and unstudied. So there is a lot to do.
Okay. And one regarding your last question, you have some bounds, right, that you use.
Yes. You want to know what they are? They are
one thing.
Yeah. So for every epsilon bigger than 0, you remember there were these M, N, and S. So you can get I'll tell you exactly. 1 second. I wrote this down. You can get every S columns are linearly independent, where S is at least M to the 1 plus epsilon over N to the epsilon. And the operator norm of B, L to N to L to M, 1 over epsilon times root of N over. Mm-hmm. So I think what was enough for our application was M squared, M cubed over N squared. So or take epsilon equals 1 even, I think. In this, but this is what we use, yeah. So then, you get that the operator norm of B is less than the smallest you can hope for, root n over m, and every s, which is of order m squared over n columns are linearly independent. That's good enough for the application. And if you can plug this in, but it just improves constant factors. It doesn't change the asymptotics of it.
Okay, this implicitly answers the question I meant to ask. So even for this question separately has interest in its own right to find the optimal parameters, but the optimal parameters will not help you with the application, right?
Completely, I don't think they will help with the application.
Okay, I see.
Maybe if somebody changes the strategy, it will become relevant. Okay, but with this induction, where you lose a constant factor at every step, you're gonna lose little O terms. Maybe you'll improve the little O terms. But even the dream bounds that I have will not get rid of them using this strategy. But it could be that if you change the strategy and also solve the question, then it will be relevant. But in my opinion, it's just a very nice question. You have a matrix, m by n matrix. Every s columns are linearly independent. The operator norm is the smallest possible you can hope for, which just comes from the fact that no column is 0. So you can get root n over m. How large can s be? And that's the random 0-1 matrices that we look at and people look at in coding theory. Maybe they're the best. Maybe you can do something better. Maybe there is some deterministic construction. That's a. But yeah, I do not have I cannot promise an application off the shelf. I think it would be it's likely. It's first of all interesting for me independently as a problem in linear algebra or operator norms. But I would not be surprised if in one of these days when somebody figures out a modification of the strategy, that you would also need the optimal S. So it could become relevant, but I didn't do that work.
Okay. Any final questions, remarks?
So this S was obtained by random construction, right?
Yes.
Was it like plus minus 1 only? No.
So you take a random 0-1 matrix where so the columns, the columns are independent of each other, and you obtain each column by doing a random walk on the hypercube, starting at 0 for m steps. Okay, so I need to give you n for every column. I have a vector of length m of 0 and 1s. I start at 0 and I do a random walk on the hypercube m steps. And then the proof is in the paper. You can just you check that this gives these parameters that I said. And that's good enough for us. Now it might be optimal, I don't know, but that would be also very nice to understand. Or maybe you can do something better, maybe not random. But yeah, Beatrice, I didn't do any work that says you're going to get an application from this. I just think it's a good question. Hopefully it's a good question.
Okay, so if there are no more questions, let's thank Assaf. I forgot to say it when you just finished. And we'll see you next week. We have 2 more talks for this term. Thank you very much, Assaf.
Thank you.